So the Hamiltonian Yeah, so we have this expression for the Hamiltonian, and as you see, we have Px, Py, and Pz that are the three momentum operators that are the same operators that were found in the free electron, the pure free electron case. We have an additional Y operator here. Due to the presence of this Y operator, we have that the Hamiltonian may commute with so you expect to have a commutation with Px and Py due to the but not with with Px and Pz, but not with Py due to the fact that you have the Y coordinate here. So you lose the capability to have this commutator equal to 0 also for the Y component as you have in the free electron case. You keep just the commutation with two components of the momentum operator. As you have a commutation with the X and Z component of the momentum operator, you expect that along X and along Z, you may have a conservation of the momentum of the electron. So you may apply along the X and Z component what was found for all the three components in the free electron case. So due to that, one tries to rewrite the wave function of the electron as, let's say, not A, because A was the vector potential, let's say C, just a coefficient, and then we have the plane wave part related to the X component, the plane wave part related to the Z component, and another part related to the Y that for the moment is left there. So at this point, when we apply the this Hamiltonian to this wave function, each time we apply the X operator or the Z operator, then we have the corresponding X or Y value. So what we expect to have here is that just I will replace Px with the corresponding Px value, and I will replace Pz with the corresponding Pz value. So after the application of that, we have 1 divided by 2m. Then I have Px, that is just a value, minus Eby operator. Then I have plus Py squared operator plus Pz squared, a value, applied to the wave function related to the Y coordinate, and this is equal to, I just leave here a parenthesis for the energy, and then the Phy component. I have simplified, let's say, this part here of the wave function, which is found both on the right side and on the left side of this equation, so I have simplified the phases here. Due to the fact that for the X and No, wait. I was anticipating something, so I just write. Sorry, I just write here this value. Then, in this case, I have here a term including an operator acting on phi y, another operator acting on phi y, and the number. So I take the number on the other side, and so I am left with 1 divided by 2m. Sorry, I forgot the square regarding px minus eby. So I have px minus eby operator squared plus py operator squared phi of y, that is equal to energy minus pz squared divided by 2m times phi y. So if you notice, at the end, this means that along z, nearly you have no change. So you do not expect that the magnetic field applied along the z direction will change the energy of the electron, since here what you have here is just the free electron expression related to the z component. So you expect that if the energy changes, will change due to some contribution of the x and y components, but for what concerns the z component, that is the component of the application of the magnetic field, the result is the same result you would have obtained for free electrons. Now, we just switch the order of these terms here. So I have py squared divided by 2m plus, I change the order of the elements within the parentheses. So 1 divided by 2m eby operator minus px squared. Then I take E and B out of the parentheses, and this, sorry, oops, this is applied to phi y. So this is equal to py squared divided by 2m. If you take EB out of the parentheses, you have E squared B squared. If you remember, the cyclotron frequency is EB divided by m. So to have the cyclotron frequency here, I have to multiply and divide by m. So I had an m value here at the denominator, so I multiply and divide by m, so I have a mass here now. So this is omega c squared, and then within the parentheses I have y minus px divided by eb. This is all applied to phi y. So at the end we have py squared divided by twice the mass of the electron plus 1/2 omega c squared y operator minus px divided by eb is a constant, is a number. I call this y0. So y0 is just px divided by eb, and this is applied to phi y and is equal to energy minus pz squared divided by twice the electronic mass times phi y. So if you notice here, you have the same Hamiltonian that you have for the harmonic oscillator. So what you expect is that the energy values corresponding to the harmonic oscillators are the same energy values that you have, in the case you have a pure harmonic oscillators. So the energy due to just this term here, so the energy of the harmonic oscillator is n plus 1/2 times h bar omega c. So in this case, as a frequency for the harmonic oscillator, we use the cyclotron frequency. So these are the energy levels corresponding to the contribution of the this part of the Hamiltonian. At this point, if we sum up everything, so this E minus pz squared divided by 2m is equal to this term. So the full energy is n plus 1/2 times h bar omega c plus pz squared divided by 2m. So the conclusion is the presence of a magnetic field along the z direction does not affect the energy contribution of the electrons along the same direction, but produces the major changes along the plane that is orthogonal to the direction of application of B. Because if you notice here, we have just the Z component, and then in place of P square X and P square Y, you have this contribution. So in this case, you have a quantization, what is called the quantization of the orbits along the XY plane, and this quantization produces discrete levels in the XY plane that are indexed by n, by this integer. And just to have an idea of what may be the value of n when we consider levels that are close to the Fermi energy, we may just evaluate h bar omega c. So just to see what is the value of that term. And h bar omega c, where omega c is EB divided by m. So if we put E the electronic charge, m the electronic mass, and we set B equal to 1 Tesla modulus, then what we have is that h bar omega c is of the order of 10 to the minus 4 eV. So this means that if you want to fix n so that the h bar omega c n plus 1/2. So if this has to be over the order of some eV, as it is in the case of Fermi energy, then n is expected to be large, very, very large, because if this is 1 eV, you have 1 divided by 10 to the minus 4. So n is of the order of 10 to the 4 in this case. So the quantum number, the value of the quantum number you use here to obtain energies that are of the order of some EVs is at least of the order of 10 to the 4. So you have not small values of the quantum number, but in general you expect to have here very large values of the quantum number. And what is the effect of this quantization mechanism on the electronic levels? I'll try to do my best to make a drawing that represents the result, but please also use your imagination. And at the end, I will ask you if everything is clear or not. So the result is the following. So if this is the Z direction, so we have the three orientations. For free electrons, what we have is that in the reciprocal space, maybe it's better to write kx, ky, and kz, so it's clear that we are in the reciprocal space. So in that situation, we have that the levels can be grouped into spheres, because you have that the occupancy of the levels is, the energy has a spherical symmetry. So when you occupy the levels, you follow, you partially fill the spheres. In this case, the energy of the system is so nothing changes along the z direction but along the horizontal direction that is on the XY plane, you have that the levels are grouped into circles, because if you fix n, you may, to see what the effect of this is, you may, let's say, approach the problem in this way. If I fix the value of n, then I have a value of the energy. What are all the levels that has in the free electron picture exactly the same energy? At this point, you may say that if you fix n, all those levels are found into a circle, because the energy dependence in the free electron case, just in the XY plane, is again symmetric with respect to the vertical axis. So if you fix the value of the energy, it's just like as if you fix the value of the modulus of K in the XY plane. So at this point, even if now this drawing is exaggerated, so to each value of n correspond a circle in the XY plane. And a circle in the XY plane, if we also consider the contribution of the Z component, then becomes a cylinder in the three-dimensional space. So the idea is, so the idea is that this quantization with the quantum number along the XY direction and a second quantum number along the Z direction produces the fact that depending on n, in the reciprocal space, you have a family of cylinders. And n allows you to access each of those cylinders. So the electronic levels are grouped into these cylinders. And I know that the drawing is terrible, but do you, let's say, are you able to make this picture in your mind, or is there some detail I may add here to make the picture more clear? Because apart from the calculations, then the final result of this model mainly depends on your capability to visualize those cylinders. So please tell me whether everything is clear, or if you have questions or comments concerning this structure.
To me, the structure is clear.
Okay, thank you for comment. Okay, so at this point, what let's say, what happens if we consider the this family, this grouping for the electronic levels, and the fact that in the free electron picture, so in the starting picture of this problem, we have in the reciprocal space a Fermi surface that for simplicity may be a sphere. So if we have this sphere, Okay, so if we have this sphere and the and this is the vertical axis, so Z, we have that we may evaluate the intersection between one cylinder and the Fermi surface. And you may do the same evaluation for all the other cylinders. So if you fix B, so if B is fixed, H bar omega C is fixed because omega C depends only on B. So at this point, you may access all the cylinders just by using the index N. So you have this family of cylinders, and the spacing, the energy spacing between one cylinder and the next is equal to H bar omega C. All the intersections will be, let's say, circles. So the intersection will be a circle, larger or smaller depending on the size of the diameter of the cylinder. And in general, or the intersections give rise to these circles that are more or less equivalent with each other, because the only thing that changes is the radius of the circle, but they are, all of them are circles. The only circle that is peculiar is the one that you may obtain when you make the intersection between the cylinder that is exactly tangent to the sphere. Because if you consider a cylinder that is exactly the same radius of the Fermi sphere, then the equatorial intersection will be larger, because in this situation you have many points of the Fermi surface that are quite close to the cylinder. So the only cylinder that is remarkably different from, the only intersection that is quite different from in general, all the intersections, is the intersection you have on the equatorial plane of the sphere, because that intersection is expected to have a larger width. Why I focused on the width? Because if you concentrate on the number of electrons that correspond to the intersection, in general, the intersection is a circle. So more or less, the number of electrons that you have on those circles are not exactly the same, but more or less similar. But if you consider the number of electrons that correspond to this intersection, the equatorial one, then the number of electrons that correspond to this intersection is larger than with respect to the number of electrons that correspond to the other intersections. So on the equatorial plane, you have a huge number of electrons that may correspond to a specific intersection. Now the question is that intersection always there? The answer is no, because let's say the diameter of the cylinders in energy depends on N and on the cyclotron frequency. So if you change B, you may switch from tangency condition to non-tangency conditions. So this equatorial intersection appears and disappears depending on B. So this intersection the equatorial intersection appears and disappear depending on B, because the radius of the family of cylinders is proportional to B through the cyclotron frequency. So this means that if you change the value of B, you may switch from tangency condition to non-tangency condition. So you have that this equatorial intersection appears and disappears depending on the value of B. So that's why they observed an oscillating behavior when they measured the macroscopic properties as a function of 1 over B. Because, let's say, at the moment, I have not explained why as a function of 1 over B. But with this scheme here, just tells you that you expect to have a modification of the macroscopic property due to the fact that you have that a huge number of electrons here that correspond to this intersection appear or disappear depending on the presence or the absence of the intersection. And please note, by saying appear and disappear, I don't mean that the electrons are removed or included in the system. So that's not the point. The point is that the electrons are always there, but what changes is just the area of the intersection. So all the electrons that belong to the intersection, you may consider that behave in the same way. So you have this huge group of electrons here that is found or not in the system depending on the value of B. Now the point is, may we translate this graphical indication into an equation that explains why we have this dependence over 1 over B. The contribution of that was due to von Sager, and he exploited the fact that N, in this case, when you consider the quantization of the orbits in the levels, sorry, in the XY plane, the N index you use here, the quantum number, is very, very large. So due to that, you may use the Bohr correspondence principle that tells you that if you consider the energy difference between two levels, two closed levels, here I have the energy corresponding to Sn plus 1 minus the energy corresponding to level n, then that should be equal to h times the frequency of the classical motion of the electron corresponding to those levels. So in this case, in place of the frequency, I just write 1 divided by the period. Why I wrote 1 divided by period? Because for block electrons, we have an estimate of the period of the motion of the electron along the trajectory. And the period was obtained when we consider the when we consider the semi-classical equation applied to used when just the external magnetic field is applied. And in this case, the period was h bar squared divided by EB times a small variation of the area divided by a small variation of the energy. So I replace this expression for T here. So I have H divided by h bar squared over EB, then delta A divided by delta E. Since the difference in energy here is quite small, this delta E and this delta E are, let's say, can be chosen to be the same. So if you don't mind, just to be able to simplify the Planck constant, I replaced this h bar, this h by h bar times 2 pi. So I write h bar times 2 pi, then I have h bar squared Then EB is here at the numerator. In place of delta E, so small variation of the energy, I write as it was before, En plus 1 minus E of n. And in place of small variation of the area, I write area corresponding to n plus 1 minus area corresponding to n. So this term and this term here can be simplified. So we may also simplify this h bar with the h bar square at the denominator. So at the end, we are left with the fact that a n plus 1 minus a corresponding to n is equal to 2 pi EB divided by h bar. So the conclusion is, if you switch from the, if you remember, A is the area of the intersection. So A n plus 1 is the area corresponding to the intersection between the Fermi surface and the cylinder corresponding to index n plus 1. And A of n is the same area, but in this case you consider intersection with the cylinder corresponding to the index n. This expression tells us that the areal variation when you switch from n plus 1 to n is constant. So doesn't depend on any feature of the electron or of the system, nor no dependence on the wave vector. It's just a constant term that depends on B, just on B as an external parameter. So the fact that this is found enables us to write down that E of n, so a general value for the area of the intersection, is equal to this 2 pi EB divided by h bar times an index n. So areal density is a multiple integer of this value plus what is generally called labeled as lambda. So this is the equivalent of the 1/2 in the energy of the harmonic oscillator. It's just to say, I don't know what is the minimum value. I just put there lambda to access the minimum value. So this is just to say, okay, I know that the areal variation is an integer multiple of 2 pi EB divided by h bar, and then I added this constant term just as an initial value for the area. At this point, if you remember the picture that I presented to you before, what is the area that is of interest when we consider the intersection between the family of cylinders and the Fermi surface? Is the area that corresponds to the Fermi surface. So is the lateral, is the maximum area that you may consider. So due to that, in place of writing in a general A of n, I write A of EF. So what we need to consider is the area that corresponds to the Fermi surface. So we will have that this is equal to pi EB divided by h bar, the index corresponding to that intersection, plus lambda. Okay? At this point, we may take on the left side B, so we have 1 divided by B is equal to 2 pi E divided by h bar area corresponding to the Fermi surface times NF plus lambda. So what tells us this equation? That if you consider 1 over B, this equation tells us that, let's say, if you fix the Fermi surface, then this term is fixed. So once you have fixed your system, this is just the coefficient. What you have here is just the coefficient. So the intersection depends on N and on B. So these are the two parameters that rule the possibility to have an intersection. So if you may find that an integer value of NF corresponds to 1 over B, then you have the intersection. Otherwise, if this value of B corresponds to a value of NF that is not an integer, then you have no intersection. So the conclusion is the variation of 1 over B corresponding to two intersections separated by just one value, one variation of the integer equal to 1 is equal to 2 pi e divided by h bar, area of the Fermi surface. So the idea is, if you observe the intersection, the equatorial one, corresponding to a fixed value of NF and to a value of B, then to jump to the next intersection, so the variation of 1 over B that let you jump to the following intersection has to be equal to this term here. So if you notice, the variation in 1 over B is just a constant term. So this is fixed, does not depend on B. So that's why you have a periodicity of the phenomena that you observe as a function when you apply an external field. And this periodicity depends not on B, but on 1 over B. Okay, is that fine for you? So is this last step clear for you? And
Sì, sì, è chiaro, però posso chiederle una cosa?
prego.
Delta è il valore iniziale, giusto che me lo sono perso?
Qual è questo delta qui?
Delta, scusi, il coso, lambda.
Ah, lambda, sì, 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 sì.
Okay,
È come
perfetto,
dire
grazie.
la scala dell'energia dell'oscillatore armonico parte da un mezzo, qui la
Certo.
scala delle aree parte da lambda,
Ok,
moltiplicato per il coefficiente 2π greco e b su h tagliato.
ok, grazie.
Yeah, and since the intersection that gives us the greatest contribution is the equatorial intersection, what is a feature that let us identify clearly the equatorial area? The feature of the equatorial area is the following. If you consider, yeah, the intersection between if you consider the different intersections the equatorial intersection is the intersection that corresponds to the maximum area. So the equatorial intersection is also called extremal area, as the extremal area is obtained in this way. If you fix the direction of the axis of the cylinders and you plot the area of all the circles that you obtain by the intersection, then the equatorial area is the area that corresponds to the maximum value of the area. So that's why it's called extremal area. Because if you make a plot of area as a function of the height of the intersection, you find that when the height corresponds to the equatorial one, then you have the maximum value of the area. Please note that there is a specific case, and just to conclude the comment. So in this case, what you obtained with this measure is that the period of the oscillation is related to the extremal area. So if you measure the period, you measure the extremal area. So this can be measured. So the idea is, if you change the orientation of B, you measure the extremal area along the plane that is orthogonal to B. So you make a sort of tomography of the Fermi surface, because the orientation of B identifies the plane that you use to make the intersections, and for any fixed orientation of B, you find what is the maximum value of the area of the Fermi surface in a plane that is orthogonal to that direction. So if you rotate B in all possible directions, then you measure the extremal area in all possible directions. So at the end, you do not know the size of the Fermi sphere. So you do not have a number that is, for instance, size or shape. You just know the value of the area. But you may try to reconstruct the full area in the three-dimensional space. In general, what one does is, step one, develop a theoretical model for the calculation. Step two, find some indications concerning the shape. Step three, go to the lab, measure an effect that is obtained in the Husband-Alfvén configuration, and depending on the variation of the extremal area, depending on the direction of B, then try to adapt your theoretical scheme to the experimental finding, depending on the value you have obtained through the measurement. So you need to have some hints concerning the shape of the surface before going to the lab and make the experiment. But so due to the fact that at the end you have just a measure of the area, you have not a size, you have not a length, you have just an area. But there is a specific situation that I would like to show you, and the situation is the following. If we consider not a sphere, but we consider, for instance, the Fermi surface that we have observed for noble metals, in that case, let's say if this is the sphere that we have for free electrons, in the case of the noble metals, we have the appearance of necks. Here, for simplicity, I make just a couple of those. So here you have necks. Necks that are due to the interaction between the sphere and the Bragg planes. If you notice, in this configuration, you have two extremal areas. One is the equatorial one. The other one corresponds to the area of the neck, because also in this case, you have a tangency condition. So you have one tangency condition and another tangency condition that is 2. So you have the equatorial extremal area, but you have also the neck extremal area, due to the fact that the periodicity is inversely proportional to the extremal area. This contribution 1 gives you a short more that range, a short scale periodicity. 2 gives you a long scale periodicity, where in this case the scale is over 1/b. So the fact that they observed a double periodicity in the experiment was an indication of the fact that in that case the shape of the Fermi sphere, the shape of the Fermi surface was not a sphere or something similar to a sphere, but was a surface with some necks or some distortions so that a double tangency condition could be obtained. So in this case, you have that the family of cylinders may give you a resonance both corresponding to the neck and both corresponding to the equatorial plane. The last question is it always possible to observe this effect? The answer is no, because now I make just an expansion of what you have here. So if you consider just this small portion, so you have the Fermi surface here, then you have one cylinder and another cylinder. If you want to observe the oscillation, this means that you need to distinguish the intersection between this cylinder and this cylinder, because as you change the value of the external field, for instance, if you increase the external field, this cylinder, let's say, there will be one cylinder in tangency condition, then as you increase the field, the cyclotron frequency changes, so the family of cylinders expands. Then you have a moment where you have no intersection, and then as you increase B, you have another intersection. So to distinguish these two intersections, so to distinguish means observe the oscillation. Now, if you remember, the Fermi surface is not a mathematical surface, has a width, and the width of the Fermi surface depends on the temperature. So now I make an exaggeration. If T is low, so if T is low, then you have one cylinder here and one cylinder here. So, okay, you distinguish the intersection, because when this cylinder is in resonance, is in tangency condition, then the other cylinders are far away. So when that cylinder is removed from the tangency condition, then you have no intersection. And then when you increase B, then the second cylinder is in tangency condition. So you switch from tangency to non-tangency in this configuration. But if you consider high temperature, now I exaggerate the result. So if you are in the high temperature limit, then the width of the Fermi surface is so broad that you do not observe any change, because within the width of the Fermi surface, you always have some cylinders. So in this case, no oscillation is observed. So the requirement is that the width of the Fermi surface and the width of the Fermi surface is of the order of kBt. So the width of that should be smaller than the difference in energy between the family of cylinders. And in that case, the difference in energy is h bar omega c. So this condition has to be fulfilled so to observe the oscillation. In this case, we know that h bar, as I told you before, this term here is of the order of 10 to the minus 4 eV. So the conclusion is I may observe this effect only if I go to low temperature, because when T is 300 K, kBT is of the order of 0.025 eV. So we are we have a value that is of the order of 10 to the minus 2. So we need to decrease the temperature of at least 2 orders of magnitude to observe this effect. And the result is that T, if you apply a magnetic field, so if B is 1 Tesla, then T should be smaller than 1.3 Kelvin. So very low temperature to observe that. You may, let's say, what you may do is, since omega C is proportional to B, you may increase B. So if in place of 1 Tesla, you put there 10 Tesla, then from 1.3 you switch to 13. So that is easier to be obtained. But in general, do not expect to observe that at room temperature. You have to cool your system down to low temperature so to observe this kind of oscillation. So this is just a requirement related to the fact that you need to be able to observe, to distinguish two different intersections, so to observe the oscillation. Okay. Do you have some comments or questions concerning that? So this is just a tomographical method to access the Fermi energy, but it is at least one direct method to access the shape. We saw another method yesterday that was the one related to the measurement of the resistivity in presence of an applied field. Also, that gives you some indications concerning the Fermi surface. That indication is more rough than the indication given by the Hahn-Vanhoffen effect, because with the measure of resistivity, you just detect the possible presence of open orbits, but you do not have any clue concerning the shape of the surface. Here, at least, you have different values of the extremal area, so you have more details concerning the shape. So this is just to say, it is possible to compare the results of the theoretical model with some experimental data, and those data can be, for instance, acquired using the Hahn-Vanhoffen effect, or in general, experiments performed in the Hahn-Vanhoffen configuration. This is the last topic concerning the application, the use of the semi-classical model in the case where we consider the dynamics of the electron. Starting from next lessons on next Monday, I will just give you a short indication of what changes for what concerns the optical properties of the Bloch metals, so metals described by the Bloch theorem. And after that, I will switch to a differently new topic. So please, in case you have some questions or comments concerning all this part concerning the use of the semi-classical equations, please let me know, and we may, for instance, discuss that on Monday. There will be also other situations where we may do that, but if you have the opportunity to have a look at the notes, we may discuss about the application of those equations next Monday.